kick on in just a second, I think. Okay, so I think we're up and live and running and all that fun stuff. All right, guys, so here we go into section 5.3. Now, this obviously didn't translate quite right. I've got this big weird box in the middle here that I don't know that I can get rid of. So, oh, I can't. I lied. My problem is that that particular thing right there didn't work. So can I get that to go away? Nope, I don't think that I can. All right, we'll come back to that box in just a second right here, guys, and we'll work on that when we get to it. All right. Now, the big thing for section 5.3, everybody, is that if we're looking at this the way that your author wants us to look at it, we need to completely ignore, for the time being, everything that we did in sections 5.1 and 5.2. Now, those two sections, you will recall, focused on the idea of approximating the area underneath a curve. And we did so with 3 different rectangular approximation methods, left, right, and midpoint, and also a trapezoidal approximation method. Okay, so we had all different ways of doing that. Then in 5.2, what we started working on was a concept called the development of the definite integral. And at this point, everybody, if you can ignore what you may have learned last year, and maybe you still remember and maybe you don't, all that a definite integral was, everybody, which was this symbol that looked like this, but with an A and a B for a lower limit and an upper limit of integration, this was just a fancier way of writing an infinite sum. That basically this symbol that we used right here was synonymous, okay, the same thing as the limit as n approaches infinity of a summation here from like k equals really wherever you wanted. We'll go with 1 up until n. So letting n approach infinity meant that the number of terms we were dealing with was going to increase without bound. And the big idea from 5.2 was that the more rectangles we use to approximate our area, the more accurate that approximation is going to be. The downside, of course, it took a lot more work to do 50 rectangles rather than 5. It took a lot more work to do 500 or 5,000 or 5 million rectangles. We cheated that a little bit because of modern technology, and we were able to use our calculators to do that just as quickly, whether it was 5,000 or 5 rectangles. Back in the day, it was a lot of work. So we're getting towards, and this is what we're going to hit in 5.4 and 5.5, we're getting towards the fast way of doing all of this information right here, but we don't know it yet. And when I say we don't know it, I mean that the old people on the wall up here, okay, Descartes and Fermat and Leibniz and Newton, they were kind of working on this, but they didn't quite have it down just yet. So what we're going to talk about in 5.3 right now is really distinct from what we did in 5.1 and 5.2. So put all that out of your mind. The title of 5.3 here is the indefinite integral. And what we have right here is not meant to be anything groundbreaking right here, but just a little notational clarification. What we're going to start using in this section is capital F when we're talking about derivatives. So capital F of x is just a random function. And you'll notice the derivative sign right there, which I'm going to undo because it got in the way. But what that first expression on the left means is the derivative of capital F of x is equal to lowercase f of x. Now, we normally talked about how we took the derivative of little f of x and called that f prime. So there's kind of a notational hierarchy that is being established right here. And you start with capital F of x, okay? And you guys know I like to use dotted lines for my derivative. The derivative of capital F of x would be either capital F prime of x, that's prime right there, or you could just call that, little f of x. And then the derivative of that would be, you could either call that derivative capital F double prime of x, or f prime of x. And we'll cram that in there. All right, sorry, hopefully you saw that and wrote that down maybe a little bit more clearly than I did right there. So all this first line is meant to convey here is that we are now defining little f of x, this right side here, to be the derivative of capital F of x. And now, just a clarification of some terms right here. So this shouldn't shock you if you understand the prime notation, which I know you do because we've been working it all year. Little f of x is the derivative of capital F of x. Okay, that just says in words what that top line there said symbolically. But now there's a new phrase being introduced here on this third line. If, let's go back to line 2, if little f of x is the derivative of capital F of x, then we can flip that around a little bit into this third line. Capital F of x right here is called an antiderivative of little f of x. And that really is the phrase of the day, guys. The title of this section, you're noticing right here, is called the indefinite integral. Really, another word for that is antiderivative. And if you think about what the prefix anti means, it actually has two meanings. I would say in English, but I think we stole that from Latin. Anti can mean directly before something, right? I'm trying to think of an example of that. All I can think of is one from Spanish. Anteojos, right, I think is the word for glasses, which means before the eyes. Anyhow, the other meaning of the prefix anti is against or opposite. From. And so in that context right here, an antiderivative is the opposite of a derivative. And so what was supposed to show up in this box right here, but did not, everybody, I'll go ahead and draw this in by hand right now. Let me put this in blue. All right. And what we've got here is a notational introduction. Now, this symbol you are familiar with. It's the same as the symbol we used right up here for a definite integral. But today, intentionally, we're leaving off the a and the b, which are the limits of integration. The a and the b make that, and that, I mean, in the top right corner, a definite integral, which is what we were playing with in section 5.1 and 5.2. Today, we're leaving it off, and this is what we call an indefinite integral. So the indefinite integral of little, that was bad. All right, let's undo that, and that, and that. Let's try it again. The indefinite integral of little f of x taken with respect to x. What that means, everybody, what that's asking for is the indefinite integral or the antiderivative of this function. We're asking ourselves now, what function can we come up with that has a derivative equal to this integrand here, f of x? And if we go back up to the notation that we introduced right here, capital F of x is an antiderivative of little f of x. So this is going to be a capital F of x right here. This is kind of the opposite of the way we wrote it before. The derivative of capital F would equal little f, but the antiderivative of little f would equal capital F. Now, there's a little problem at the end right here, and I don't know if you guys noticed it or not. I hate to sound like an English teacher, but here we go. There are only, what, 2 articles in the English language, okay? The and a, although a and an if it's followed by a vowel or a vowel sound or whatever, but there's really just 2. And I don't know if you guys noticed here, this was not a mistake right here. We said the, that's not what I wanted to say, the right there. Little f of x is the derivative, meaning the one and only of capital F of x. If you guys think back to everything we did in chapter 3, all the problems that we had, the directions always said, given a function, find the derivative. And there was one and only one right answer to all of those problems. That's what the implies. There is only one right answer. But now, maybe you noticed, and hopefully you did now that I brought it up, the third line, capital F of x is an antiderivative of f of x. And the reason for that, I don't know if you guys have thought this far ahead just yet, but the reason for that deals with something that comes at the end of capital F of x here called a plus c. And sorry, that's a little tough to see here. C is called the constant of integration. Let me give you a quick example of what I mean right here. So if we were to start, and you guys don't need to write this down, this isn't hugely important, but if I was going to give you something like little f of x is equal to, I'm going to go with 3x squared Let me just go with 3x squared plus 2x minus 7. We'll go with a quadratic trinomial right here. In the first semester, in chapter 3, I would ask you guys to find the derivative of little f, which of course we just got used to calling f prime. And I think everybody here's got it, right? We're going to go ahead and we're going to differentiate both sides just using the power rule here. So good news, nothing's changed. And we're going to get a 6x plus 2. Weird. Been a while since I've done a derivative, but it tends to stick with you. So that's how we go down a level right here from f of x, I should say from little f of x to little f prime of x. But now if I ask you to go up a level, the notation we would use here now, guys, for a function that is higher in complexity than little f of x would be capital F of x. And now if I were to ask you guys to anti-differentiate this expression right over here, the question now becomes, what is a function that we can come up with that will give us f of x for our derivative? So, since this is rare and I'm recording this and we're live and you guys are here with me, anybody think they know? Let's just go term by term. What individual one-term expression, monomial, would give us a derivative of 3x squared?
X cubed.
Gabe, x cubed. Well, I'm not sure that Gabe is right, so I'm going to write it down, x cubed, and now I'm simply going to think about that by saying out loud, and you think about it too, is it true that the derivative of x cubed is going to get us 3x squared? What do you guys think?
Yeah.
Works for me. Okay, so we got that one right. Now we keep going term by term. How about an antiderivative of 2x? What function could we take the derivative of and end up with 2x?
X squared.
Joel says x squared. So if I put a plus x squared here, that derivative right there, yeah, would get me 2x. So we're in pretty good shape. How about our third term, guys? Let's anti-differentiate the -7. What function in the first semester could we differentiate to get a derivative of -7?
-7x.
-7x. Let's see, derivative of that, yeah, would get me -7. So it kind of feels like we're done. There's only one little problem. And does anybody think they figured out what it is already?
Any constant would end up just not existing if you take the derivative of it.
Yeah, that's right, Quinlan. Basically, when you differentiate a constant, it vanishes without a trace. Quinlan, what's your favorite constant?
27.
Okay, so Quinlan's point is that there could be, in this top level function, capital F of x, there could be a plus 27 at the end right there, all right? And if that were the case, the derivative of that plus 27 wouldn't show up here at all, because the derivative of any constant, 27, -5, pi, e, all right? The derivative of any constant is always going to end up being 0. And so for that reason, it's impossible to know if Quinlan just guessed right by putting a plus 27 there, or if it was a different constant, or if there wasn't a constant at all. So there is absolutely no way of knowing if there's a constant there in red, and if so, what it is. So that's why we don't try to guess. We generically just put a plus c at the end of our antiderivative expression, indicating that IDK, all right, I'm not sure if there's a constant there or not. Now, what's important to note, everybody, if you look at the three things we have written on this page, f prime of x is absolutely 100% certainly 6x plus 2. No question about that. F of x, the middle line, is absolutely certainly 3x squared plus 2x minus 7. I know because I made it up and I gave it to you guys. But the point there is that there are how many different possible functions that could serve this purpose or fill this pattern of capital F of x?
Infinite amount.
Yeah, Joel, there's an infinite number of constants we could put at the end of that, and each one of them makes capital F of X slightly different. So that is why we say, let's go back to this article game, F prime of X is the derivative of F of X. It's the only one possible answer, 6X plus 2. But what we've written here for capital F of X is an antiderivative of little f of x right here. Because with that plus c, that actually means there's an infinite number of correct answers.
So are like the derivatives and antiderivatives just like inverses of each other?
That is exactly what it means there, Joel. Exactly. Derivatives and antiderivatives are inverse operations of one another. Okay. The word anti meaning against or opposite. So in a way, I guess here's what they're saying. You guys know very well, and you've known for, I don't know, 6, 7 years, that the inverse operation of addition is subtraction. But I guess using the same name game, what's something else they could have called subtraction instead of making up a new word?
Anti-addition.
Anti-addition. Division could be called
Anti-multiplication.
anti-multiplication. That's right. Square root could be called
Anti-squaring.
anti-square. Yeah. Here's a fun one. The inverse of sine could be called
Was it anti-cosecant?
No, you're thinking too hard there, Gabe.
Okay.
I don't need the reciprocal of it.
Anti-sine.
Anti-sine. But then again, guys, we kind of have a word for that.
Oh yeah. Inverse
What's
sine.
that? Inverse sine, or what's the other one that I don't use very often?
What? Isn't like arc sine or something like that?
Yeah, arc sine. Arc sine means that exact same thing. Okay, so that page right there, I told you guys you didn't need to write that down. If you did, though, that might be just a very clear paradigm type example for you guys to have in your notes somewhere, just to kind of clarify what's going on. But anyway, hopefully that helps. Okay, that is messy on the first page, but that's really as much as I wanted to do with you. The rest of this is going to go pretty quickly, guys. That's really the only conceptual understanding that we need to come to here in section 5.3. Now I think I have 5 or 6 examples for you, and then we're done. So let's get rolling here. The directions: evaluate each indefinite integral. But of course, an indefinite integral is the same thing as an antiderivative. So our integrand here of 5x minus 3, we are asking the question now, what is a function that we can come up with that has a derivative of 5x minus 3? Now, in the example that we just did, you guys collectively, each one of you did a different one, you were able to come up with these 3 terms, and I didn't really press you guys as to why or how. That always worries me that some of you get it and that some of you aren't quite sure, and you're just sitting there in awkward silence. So humor me for just a second. I know some of you probably know the answer, but I'm worried some of you guys don't, but let's talk about it. With 5x minus 3, that is a polynomial function. When we take the derivative of polynomials, we use the power rule, term by term. Now that we're anti-differentiating, we're simply going to reverse the power rule. So the first term, 5x, we're going to keep the base the same, which is an x. Now, reversing the power rule, okay, we are going to do 2 things. We are going to raise the exponent by 1, and then instead of multiplying, we're going to divide by that new exponent. So we had x to the first, we raise it by 1, and it now becomes an x squared. Then we take the existing coefficient, 5, and we divide it by the new exponent. And I made this one messy on purpose. The 5 doesn't divide evenly by 2, and that's fine. So we'll just leave that as 5/2 x squared. Now, the great thing about anti-differentiating, guys, it's really easy to check your answers if you're not being lazy about this. If I were to take the derivative of 5/2 x squared, I would use the power rule. The first thing I would do is I would multiply the existing exponent times the existing coefficient. The 2 times the 5/2, the 2's would cancel, and I would get 5. Then the only other thing I have to do is take that exponent and drop it by 1. So we would get 5x. And sure enough, that's the term here that we were trying to anti-differentiate. So if you notice, I did the opposite two things in the opposite order that I normally do in the power rule. Normally, I multiply exponent times coefficient and then drop the exponent. Reversing it, I raised the exponent first from 1 to 2, and then I divided the existing coefficient by the new exponent to get 5/2 x squared. And then really, it's the same thing here, guys, the minus 3. Now remember, that is actually minus 3 times x to the what power?
1.
No, that is not right now, and that's negative.
Zero,
There's
zero,
no
zero.
x.
I said 0.
That's x to the 0. So if it helps, I don't know that you guys are going to need this at all, but you could write an x to the 0 right there, and now try to reverse your rule from there. Start off by raising the exponent by 1, so that is going to be x to the first power, and then divide the old coefficient, 3, really negative 3, by the new exponent, which is a 1, and that's going to be a minus 3x. And sure enough, double check, the derivative of minus 3x, yeah, is minus 3, so that's good. And what's the only thing we're missing, everybody?
Plus C.
Plus C. Now, I will tell you guys, it is very common, very easy, very understandable for people to leave off that plus C. Every time you do it on a quiz or a test, it costs you a point. So that's why very often I'll see people, you know, they'll get their quiz back in the old days when we used to do things on paper, right? And they'll say, oh, man, so, oh my God. Okay, fine. There's your piece of paper. And it'll say quiz up at the top, and here's 1, and here's 2, and here's 3. And the very first thing I'll see a lot of people write on their paper at the top is plus C, like with an exclamation point at the top, to remind themselves on every one of these problems, there needs to be that plus C at the end. Questions on that, guys? Or are we feeling okay? All right, that's where we're at. Sarah, I'm just getting to your comment right now. This doesn't suit you at all. You're a total math nerd, and for you to say you're anti-math is like me saying I'm anti-bald. All right, it just doesn't make any sense. Know who you are and own it, for crying out loud. Anyway, let's move on. All right, guys, next example right here. Ooh, how about just anti-differentiating a constant? I meant for this to be something brilliant right here, but actually we've already done it within a couple of examples already. Everybody, let's go back though to something we learned at the very beginning of chapter 3. What kind of function, I'm looking for a word here, what kind of function has a constant derivative?
Linear.
Yeah, there we go. Nolan, I think that was you. That's a linear function right there. And so that kind of tells me what I'm looking for. If I'm trying to anti-differentiate a constant function, the answer to that has to be a linear function. So again, we would think of this as 8x to the 0 power, raise that exponent by 1, which is just going to be x to the first, divide the 8 by the 1, and of course we just get an 8x, and we won't forget to put a plus C at the end right there, guys. So that one is lickety split. I think you knew it already. Let me just spell it out. Anytime you're anti-differentiating a constant function, you just stick an X on the end. Okay, don't forget your plus C, and then we're good to go. Sure enough, everybody, what is the derivative of 8x plus some constant taken with respect to x? I'm going to assume that's a silence because the question was too easy to dignify with a response, that was just going to be 8. Okay, right. Next. Oh, the plot thickens a little bit. Anti-differentiating, or taking the indefinite integral of 24 times the cube root of x with respect to x. Anybody have a wild guess what we're going to do with this first?
We're gonna raise the power of the x. Wait, no. You're gonna like do the thing with the fractional exponent.
I'm going to rewrite it first, Joel. Right. And then once I do that, I'm going to do exactly what you said. So I would rewrite this now as the indefinite integral of 24 and then x to the 1/3 power. I told you guys back in the first semester that anytime you're doing a derivative with radicals, especially if it's something more complicated than a square root, that I think it's a good idea for you to rewrite that with fractional exponents. power rule just works a little bit easier that way. And the same thing applies here for anti-differentiating. So I think we're ready, guys. Let's do it. Keep the same base of your exponent, which is going to be an x. Raise your power by 1. Hey, everybody, what's 1 more than 1/3?
4/3.
Excellent. You're going to add 3/3 to that to get an x to the 4/3. And now this gets just a little bit tricky. We need to divide the existing coefficient of 24 by the new exponent, which is 4/3. So 24 is getting divided by the new exponent of 4/3. But I hope you guys haven't forgotten your 5th grade math. Mrs. Fontana would be very upset if you had. Dividing by a fraction is the same thing as doing what?
Multiplying by the reciprocal.
Multiplying by its reciprocal. So this is 24 times 3/4. And I certainly hope you guys know how to do this in your head. I think I've shown you this shortcut a couple of times. You're going to take the whole number, 24, divide it by the denominator of this fraction. So 24 divided by 4 is going to get us 6, and then multiply by the numerator right there. 6 times 3 is going to get us 18. And that is going to be the new coefficient of our antiderivative. We'll stick a plus c at the end because that's what we do. And there we go, guys. That should be our final answer. And a quick check. The derivative of 18x to the 4/3. We would multiply the 18 times the 4/3. So I'll do the same trick. The 18 gets divided by 3 to make 6, times the numerator of 4 makes 24, and then x to the 1/3 power. So we're in pretty good shape. There's one slight thing. I'm not going to say this is wrong by any stretch, but I talked to you guys about this back in chapter 3. Since the original expression right here, the integrand, was given to you with radicals, it might make some sense to put the answer in radical form rather than fractional exponents. But let me be very clear, that is not something I'm going to be taking off for, so you guys don't need to panic. But if you wanted, you could write this. Now, it's a little uglier with the 4 in there, but you could do 18 times the cube root of x to the 4th plus c, and that answer would be just as correct, maybe a little bit more in keeping with the format of the original expression that was given to us. But again, you will get full credit for either one of these two answers right here. Okay. Any questions so far? Am I going too fast for you guys, or is this not too shabby?
Nope, it's all good so far.
All right. Then let's keep rolling through it. All right, D is a little bit weird. All right, and D is actually not going to be super hard to do once we figure out how to do it. But I got to warn you guys about one thing. There is a way that you can do D pretty easily, and then there's a way that a lot of people are going to try to do it, and it's going to be super, super complicated. Let me ask you what feels like a weird question. If you were being asked to differentiate that expression right there, which is not what's happening. We're going the opposite direction, but humor me. If you were being asked to differentiate that expression, what rule would you need to use?
Quotient rule?
Good, Gabe, the quotient rule. This is written as a quotient. There's a numerator and a denominator, and there's a variable in both parts right there. So you would need the quotient rule. Now, what I've got to warn you guys about is this. There is no quotient rule for integrals or antiderivatives. There is no product rule, not really, for antiderivatives or integrals. So anytime you find yourself with an integrand that is complicated, that it would require one of our difficult rules from chapter 3, you've got to be clever in the way that we try to anti-differentiate that. You can't just plow through it and just reverse these rules that you had, you thought you knew from the past. So anybody think they know what we're going to do to rewrite this original expression in a manner that's going to make it easier to anti-differentiate? This was a trick I think we did in limits a little bit back in chapter 2.
Can you make them?
Oh, one at a time here. Sarah, go ahead.
Can you make them separate? I don't know what they're called. Separate. Can you make them separate? What? I don't know what they're called. Separate. Can you make them separate? What? I don't know what they're called. Separate. Can you make them separate? What? I don't know what they're called. Separate. What? I don't know what they're called. Separate. Can you make them separate? What? I don't know what they're called. Separate. Can you make them separate? What? I don't know what they're called. Separate. Can you make them separate? What? I don't know what they're called. Separate. Can you make them separate? What? I don't know what they're called. Separate. Can you make them separate? What? I don't know what they're called. Separate. Can you make them separate? What? I don't know what they're called. Separate. Can you make them separate? What? I don't know what they're called. Separate. Can you make them separate? What? I don't know what they're called. Separate. Can you make them separate? What? I don't know what they're called. Separate. Can you make them separ separate.
You're anti-word right now is what you are.
Yeah.
Joel, what do you think? You're on the right track, Sarah.
I was gonna say, oh, I thought we were supposed to like use a conjugate.
No, 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 no. Joel, nothing as complicated as that. What we're going to do, guys, is we're going to take advantage of a simple fact, and I'll write it at the bottom. If you know this, you don't need to write it down, but that A plus B all divided by C. What's going on there? I've got a binomial numerator and a monomial denominator. Okay, Sarah, I think you were suggesting the right thing. We're going to split this up now into two separate fractions. What's the first one going to be?
5x squared over x.
Oh, I'm sorry, I'm still on the bottom right here, Sarah, but yeah.
Oh.
A over C plus B over C.
A over C plus B over C. There we go. And Sarah, you've got it. That's exactly what we're going to do on the top. Now, I'm not even going to take the time to rewrite this because I think you guys can do it. The 5x squared over x just becomes what?
10x. Wait, no, I'm dumb. I'm sorry. Just 5x.
Just 5x, right.
I was
So-
thinking too far ahead. In my
Yes, you were. Yes, you were. That's okay. Plus, now, the second term, 6, gets divided by x. What do I write there?
Just 6 over x.
Not bad, but what's an easier way to deal with that from a derivative or an antiderivative standpoint?
I can't think of it off the top of my head.
Instead of 6 over x, I'm going to write that as 6x to the negative first power.
Okay.
Okay, so dealing with everything on one line, including fractional or negative exponents, is a better choice than the fractions when we have to differentiate, or in this case, anti-differentiate. And then a minus, oh, here's a weird one. The square root of x over x simplifies to what?
X to the negative 1/2.
X to the negative 1/2 is exactly it. Good job, Sarah. But guys, I'm going to talk about that because I think there are some of us maybe wondering how that happened. Let's go back, and I know this seemed obvious. Let's think about this first term here, 5x, which is really 5x to the first. And ask yourself, how did we get that exponent of 1? Well, you had an exponent of 2 right here in the numerator, and then you were dividing it by an exponent of 1. Okay, so going back to what my 8th grade son is doing right now in Algebra 1, when they go to divide monomials, you subtract your exponents. And that's what we did here. The 2 on the top minus the 1 on bottom got you x to the first power, top minus bottom. So everybody, this right here is x to the what power? That was not meant to be a hard question.
1/2.
1/2. This on the bottom again was x to the first. So 1/2 minus 1 is going to get you x to the negative 1/2. Okay, so that is where that came from. And I'm going to get rid of all my markings right here, which are kind of a mess. All right, but there we go. And then a dx at the end of all that. And now that we've got everything written on one line, I think we're ready to go ahead and anti-differentiate. So here we go, guys. Antiderivative of 5x. Start with your x, raise the power by 1, make that a 2, and then divide. 5 divided by 2 is just going to be 5 divided by 2. That's what fractions were invented for. So it's 5/2. All right, gets a little bit tougher here. Anti-differentiating a 6 and then an x to the negative 1. All right, I think I've stumbled on something here, but let's get to it. All right, let's try it. The first thing we do is we keep the base the same. We raise the exponent by 1, which is what?
Wouldn't it just be x?
No, it would not just be x.
It would be x to the 0 power, which wouldn't be anything.
Right.
Or-
Well, I mean, x to the 0 power is 1. That's something. But let me just follow my rules right now. 1 more than negative 1, Gabe, is 0. So that becomes x to the 0. And that by itself is fine. X to the 0 is 1. And this is how I normally end up with a constant within my answer. The problem, though, comes in now putting a plus in front of that. and taking the old coefficient, which was 6, and dividing that by the new exponent, which is 0. And right there, right, a baby seal just died, okay, or something, whatever Mr. Murphy says. All right, something bad just happened. We just tried to divide 6 by 0, and that is going to be a problem. I wasn't planning on getting into this yet today, but obviously I put it into an example. Does anybody remember a function from the first semester that we could differentiate to end up with an answer of 1 over x?
Wasn't that ln?
Yeah, Joel, that was natural log of x. That's right. The derivative with respect to x of the natural log of x was equal to 1 over x. Okay? And now, here's a little bit of weird, it's what we've been talking about, but I haven't shown it to you yet. What if I now did an antiderivative of both the left and the right side? Anybody want to guess what happens to an antiderivative of a derivative?
They cancel out.
That's exactly it. They cancel each other out, and I get natural log of x is equal to an antiderivative of 1 over x. I would just need to put a dx at the end of all that. Actually, that really should have come here and here, and then that dx cancels with that dx. But regardless, so look at this statement we just came up with right here, guys. And I really should read it backwards, right to left. An antiderivative of 1 over x is equal to natural log of x. And that is precisely the little conundrum we find ourselves in right here. Forget about the 6 for the time being, guys. That's kind of, you can just kind of tag along right. In fact, that started with a plus 6, so I'll just put a plus 6 here. What function has an antiderivative of x to the negative first, or 1 over x? You guys just told me. Natural log of x. Technically, there's an absolute value around that. We will get into that later on in this chapter. Don't worry about it too much right now. And last one then, this is a fun one. Antiderivative of x to the negative 1/2 power. Start with x, raise the power by 1, and it becomes what?
1/2.
Positive 1/2, correct. And then divide the old coefficient by the new exponent. So our old coefficient was negative 1. Let's divide negative 1 by 1/2. And what do you get?
Negative 1/2.
No.
What?
-2.
Negative 2.
I
They were
apologize.
dividing by 1/2, which is multiplying by 2. So that should be a minus 2 x to the 1/2 and a plus c at the end of that. And if you think about it term by term, guys, does that derivative get us 5x? I feel like we've seen that one already today.
Yeah, we saw
Yes,
a couple examples.
Yes, does that derivative get us 6 over x, given that we talked our way through that mess?
Yeah.
How come?
Yes.
How come you have the absolute value thing?
Sarah, it has to do with getting the domain of the derivative and the domain of the antiderivative to match. I'm not going to say more about that today because that's actually something we're going to talk about later on in this chapter. But basically, in this expression right here, it's okay for x to be negative. With this expression right here, without the absolute value, if it was just 6 natural log of x, you're limiting yourself to only positive values of x. Putting the absolute value means that you can include negative values here just the way that negative values were naturally included here.
Okay, thanks.
That's probably good for now. And in this section, Sarah, if you forget the absolute value, relax, no big deal. Here's the real kicker though, guys, let's make sure about this one, is the antiderivative of that going to equal that? Negative 2 times 1/2 is going to get us negative 1 x, and then we drop the power by 1. 1/2 minus 1, yeah, gets us negative 1/2. And I've got my plus c at the end, so I think we are good to go there, ladies and gentlemen. And there it is. Not too shabby, right? All right, three more, but I think they're going to go pretty quickly. Just to remind you guys that there are functions out there outside of the realm of polynomials, but the concept of an antiderivative is really going to be the same. So the question now is, what is an antiderivative of cosine of an angle? So the question really becomes, cosine of an angle is the derivative of what type of function?
Sine, right?
Let's go back to section 3.5, everybody. Okay, what you guys learned at the time, what you planted as a seed in your head, like the movie Inception, is that the derivative of sine is cosine. So Sarah, you're on the right track. What we came back though later and tried to adjust that mentality to is this: the derivative of sine of any angle is equal to cosine of
The same angle.
the same angle, but wait, there's more.
Plus the derivative of that angle.
Times the derivative of that angle, times the derivative within. So with that in mind, I think we've got enough to get started. Okay. Sarah, I think you had it right. Gabe, you said what you said very, very well. If we're trying to anti-differentiate cosine of an angle, cosine is the derivative of sine. So this is definitely going to be a sine right here. Let's make sure we all understand this. Of what angle?
3x minus pi over 2.
That was very weird what just happened right there. Yes, but dang gummit. Because why, everybody? What's the phrase I wanted you to say over and over again when we were differentiating trig?
Was it like that sine or that angle?
The angle,
The angle stays the same.
well, the angle never changes. It's a little more poetic that way, Joel, but you're right. The angle never changes. And the same thing happens then here when we are anti-differentiating. So it's still 3x minus pi over 2. The problem here is, guys, and a lot of people are going to say, yeah, okay, and put a plus c at the end and woohoo, we're done. Here's the problem. If you go to check your work, the derivative of this function is not going to get you this. Not exactly. So let's try it. The derivative of sine of any angle is cosine of the same angle times the derivative within, chain rule. And the derivative of 3x minus pi over 2 is
3.
3. And there's no 3 up above. Now, let me be clear. If there were a 3 here, we'd be scot-free right now, guys, because now the derivative of our answer matches the original integrand. All good. But that is not what happened here, and I can't just put a 3 in there. So can anybody think of something we can do to our answer to kind of negate the 3 that would need to show up because of the chain rule?
I don't know if you're allowed to actually. Yeah, never mind.
I'll go ahead and say it, Joel.
I was gonna say, like, you can make that plus c a -3, but I don't think you can change that.
Yeah, the problem there would be it's multiplication versus addition.
Oh, true.
They're
yeah.
not quite going to cancel each other out.
So like multiply by 1/3.
Okay, so what we're essentially talking about doing here, you guys, is reversing the chain rule. And in the chain rule, when you're differentiating, you then at the end multiply by the derivative within. So now, Sarah, we could divide by the derivative within or multiply by its reciprocal by putting a 1/3 out in front. And if you're wondering if Sarah is right, we don't have to sit here and argue about it. Let's just find out. The derivative of 1/3 sine of that angle. Well, the derivative would start with a 1/3 just because of the constant multiple rule. Derivative of sine of any angle is cosine of the same angle, 3x minus a pi over 2, times the derivative within. And the derivative of 3x minus pi over 2 is 3. And then at the end, the derivative of that plus c is just 0. And now I think you can see it. The 3 and the 1/3 cancel each other out. there's your derivative, and that is the original integrand. So yeah, guys, what we had right here was our answer. So what we just learned that you can do is we can reverse the chain rule, not by multiplying by the derivative within, but by dividing. But I've got to warn you, and if you guys are writing things down, you probably want to write this down. What we just did only works when the derivative within is a constant. And in this case, the derivative within was 3. So with a constant like 3, you can do what we did. But oh boy, don't write this down. If that was a 3x squared, okay, you could not just divide by 1 over 6x. And the reason why is that derivative would now require the product rule, which would get you something far messier than this. All right, so you may, I'm in a huge mess right here. All right, you might want to write that down. Reversing the chain rule only works when the derivative within is constant. All right, that is important, everybody. Okay, didn't mean to draw that parenthesis right there. I got 2 more quick problems and then we're done. Okay, let's anti-differentiate a cosecant squared problem. Now, I bring this up because problems like this always show up, and what people tend to do is make this more complicated than it needs to be. The very first thing you should be thinking about on any antiderivative problem is, do I recognize my integrand as a derivative from back in chapter 3? Is cosecant squared of whatever, I don't care about that right now, is cosecant squared a derivative that we learned back in chapter 3?
Of
I think so.
Kind of, right. Gabe, do you know what?
I would have to look back at my notes.
Okay. Sarah, do you just know it?
It's cotangent, right?
You're close on that one. So let me
Negative.
write something down at the bottom. What's that?
Was it negative cotangent?
I think so, yeah. So one of those 6 that we learned was that the derivative with respect to x of the cotangent of, let me just call this theta right here. Derivative of cotangent was the opposite of cosecant squared of the same angle, which is still going to be theta, but then times the derivative of that angle, so d theta dx. Okay? And that is almost what we have right here, except for the negative. So that just means that our answer, you guys, is going to begin with
Minus sign.
yeah, a negative to balance that out. Antiderivative of cosecant squared is going to be the opposite of cotangent of the same angle, which is still going to remain theta over 2. But wait, there's more. Now we are dividing by the derivative within. Everybody, what is the derivative of theta over 2?
One half.
Right. And we're going to divide by 1/2 right now. And of course, dividing by 1/2 is the same as
Multiplying by the reciprocal.
multiplying by 2. Right. So I'm going to make that a -2 out in front and then just a plus c at the end. And I think we've got it. I think that's my answer. But if I wanted to make sure, hang on now, let me draw a dotted line. Let's think about this again. Our derivative then, okay, would be -2. The derivative of cotangent of an angle is negative. There's another negative. Cosecant squared of the same angle, theta over 2, times the derivative of that angle, which would be a 1/2. Don't worry about that because it's gone. So what happens now? Negative, negative cancel each other out. 2 times 1/2 cancels each other out. And our derivative of our antiderivative is just cosecant squared of theta over 2. That is exactly what our original integrand was. So now we know, not just we think, not just we suspect, not just we hope, now we know that our answer is right because the derivative of our antiderivative matched the original integrand. And I got 2 minutes left, everybody. I had one last example to do with you. Let's knock it out real quick. Exponential functions. Guys, how do you take the derivative of e to a power?
It's e to that same power times the derivative.
Times the derivative of the exponent. That's right. So again, I have less than a minute now. Same base, e, raised to the same power of 4x minus 7. But the derivative of that exponent, 4, we are now going to need to divide the existing coefficient by the derivative of that exponent, which is 4, and a plus c at the end right there. So the 8 over 4 is going to give us 2e to the 4x minus 7, and a plus c at the end of all that. I don't think we have time to verify that one, guys, but that is where we're at. All right. Nice timing. There's the bell, guys. Let's give 5.3 a shot. Not too bad of a section. I think you guys will do great with that. All right. Thank you, everybody. Good job. And I will talk to you guys on Wednesday. Let me know if you guys have any questions. I'll get the assignment posted ASAP. Thanks, guys.
Bye.
Have a good one.